How's it going, everybody? So today I'm going to be walking you through how to download and use LTSpice, and then I'll also be talking a little bit about the lab here for week 4 coming up. Make sure you read this pre-lab materials before watching this video, since you need to understand at least the basics of voltage and current and some of Kirchhoff's laws that I'll be talking about when we use LTSpice. So to get started, we need to download LTSpice on our computer. So let's go to google.com and Google LTSpice. That'll bring you up with this window, the first link. Go ahead and click that. Direct you to Linear Technology site, and you can see right here you can download for either Windows or Mac. I haven't used Mac, LTSpice on Mac, so if you choose to if you have a Mac and you download it for Mac, you may or may not be able to follow this video. The lab computers in the senior project lab are Windows, and they do have LTSpice installed, so you can certainly go there. So if you click this download LTSpice for Windows, just say no thanks, just download the software. And that should walk you through the download process, just like any other software would. So now we want to open up LTSpice. So I have LTSpice right here. I'll open it up. And so this is what the page should look like when you first open it up. Then go ahead and click this new schematic button in the upper left. I don't know why it doesn't just start you with this when you open it up, but you need to click that before you can actually do anything in LTSpice. So now we have that new schematic. We're going to go placing components. So the first thing I'm going to build is a simple voltage resistor network. So I'm going to go over here to edit, and I'm going to click component, and that'll bring me up with this list of all the possible components that LTSpice has in its repertoire, I guess. So you can see there's some transistors here. You're not supposed to know what those are, but just FYI. What we're really interested in is voltage, and that's if you scroll to the far right, you can just see voltage source. So that's what we want. So go ahead and place that right in the center of the schematic, give or take. And it'll arbitrarily name it V1, and it has doesn't have a value yet. That's what this V means, but that's okay. So the next thing we're going to do is we need to place a resistor. So we can come up here, and I believe this is a resistor, and we can click that and bring it down here. And by the way, if you right-click, that'll stop placing components, and it'll go back. So again, if you have a component that's dragging around the screen, just go ahead and right-click, and you'll forget about it. So the next thing we need to do in order to make a circuit, if you read the pre-lab, it'll tell you that you can't have a circuit functioning, or you can't have current flowing without a connection. So we have to make a loop. So I click this wire button up here. It just says wire, and then you have this little dotted lines, and that'll just, you click, and you can drag your wires any way you want. The cleaner the better. So as you can see, I attached the positive end of the voltage source to the top of the resistor, and then I want to do the same thing for the negative side. So I'll bring that down a little bit, bring it over, and bring it up. Okay, the next thing you need, and you need this for any circuit, is you need to reference a ground. So a ground is just where the 0 volts is in your circuit. So you can define that anywhere. Actually, there's nothing wrong with defining ground up here, but for simplicity, you usually want to put it on the negative side of your voltage source. So then I'm going to go draw another wire, and by the way, there are hotkeys, so if you see me doing anything really quickly, it's probably because I knew a hotkey for it. I'll try to talk about those as I go through. So now that we have our voltage source and our resistor network, we are pretty much ready to simulate, except that we need values for these components. So I don't know, let's, for the sake of argument, choose 10 volts for our voltage source. And then on the right, on the resistor, we can choose, I don't know, 1 kilo ohm. So notice that I need to right click, and you can set values, and then you can enter, click OK, and it'll put the value on the schematic for you. And on the right, that'll do the same thing. So right click, enter the value. Don't worry about the tolerances or the power rating. That's if you have a real resistor. Those are things you might want to put in there, but for now we just need a value. Okay, so we have a voltage source set to 10 volts and a resistor set to 1 kilo ohm. So now we have a circuit that can run. The next thing we need to do is, since we're running on DC, which stands for direct current, we just need to do a .op. And what is a .op? A .op is an operating point measurement, which means it's just going to operate at the 1 voltage in our circuit. So that's going to be 10 volts. So what I did here is, let me do this again, is I click this .op, it's called a SPICE directive, and I literally just type in .op, and I click enter, and I place that on the schematic like that. Doesn't matter where you place it, just needs to be there. So now we're ready to run. So if we click simulate, run, it'll pop up with this window. And this window actually tells you something, although it kind of labels things just randomly. So VN001 means the voltage at node 1. So since it's a simple circuit, you can see 10 volts. And that's just this node right up here. You can also see that it defines the current. So IR1, which would be the current through R1, is defined as 0.01. And if you do that, that's also 10 milliamps. And you can do that calculation by hand. You can say Ohm's law, voltage equals current times resistance. And if you divide both sides by the resistance, you get V over R equals I. And if you do that math, you say 10 volts divided by 1 kilo ohm will equal 10 milliamps, or 0.01 amps. And then you can see it defines the current for the voltage source as well. You can see it defines negative 0.01. So that's just a sign. The sign on that doesn't mean that you have less than zero current flowing. It indicates a direction of current flow. So in electronic systems, or circuits rather, a current flowing into the positive terminal of the device is defined as a positive current, at least in LTSpice. And so in this case, since current is coming out of the, and I'll close this here, since current is coming out of the voltage source, following my cursor and going through the resistor and back to the negative side, this component, the voltage source, defines current as being negative, or going in the negative direction, since it's coming out of the positive terminal. So just kind of get used to that, because that's LTSpice. Now, if you can see here in the lower left-hand corner of the screen, it should show a couple different things when I hover over this resistor here. It says DC operating point 10 milliamps, like we said, and it also gives you dissipation. That dissipation is just a power rating, or rather the power that the component is dissipating. So then to the left, you can see that the voltage source, since there's only one other component, is dissipating the same amount of power, but it's dissipating minus 100 milliwatts. And the idea there is that minus 100 plus 100, you get a net dissipation of 0 watts. So that's good. And so what else? Okay, so let's work on some slightly more complicated circuits. I can delete. I just click the delete button. So if you click the delete button, it'll bring up these scissors, and you can go ahead and cut components away, cut wires away. So I'm just going to cut these wires away so that I can add it on the resistor. So another hotkey is to click R. If you click R, it'll bring up another resistor, and you can place that down and right-click to get rid of it. So now just for making this easy, we're going to put another 1 kilo ohm resistor. And by the way, the ohms isn't there, but it's implied. And then I want to draw wires to connect these components. So I'm going to click F3 again, or F3 for draw wire, or you can click on the draw wire. And I'm going to drag this up, and if you come up here and bring it over and down. Okay, and it should stop when you get to the end of a component. And then you can do the same thing here. Alright, so there's our circuit. It's just a 10 volt voltage source with two 1 kilo ohm resistors. So now, if we click the simulate, and by the way, the .op stays there. I didn't move it, it just can hang out. So now I click run, and I get a couple more things this time. So here I get the voltage at node 1 is 10 volts, so that's at this top node right here. Now the voltage at node 2 is 5 volts, so that's actually right here. And if you do the math, you'll figure out that if these resistors are equal value, it doesn't matter what values they are as long as they're the same, the voltage in between them will be exactly the voltage of our supply, 10 volts, divided by 2. So 10 over 2, 5 volts. And then you also see that since we added another resistor in series, our total resistance, or our equivalent resistance, goes up from 1 kilo ohm to 2 kilo ohms. So then you can see here that our current dropped by half because we doubled the resistance. So that's just another Ohm's law thing, and that's pretty much it for this circuit. And then again, you have the minus 5 milliamps for the component, or for the voltage source. Okay, so that's a simple series resistor network. And the next thing to do is a parallel resistor network. So let's delete these wires and click R and bring up a resistor again. We'll drag that over here. Clicking F3, I'm going a little bit faster now, I realize, so just bear with me, you can pause the video. I'm going to connect all these lines, make sure you bring everything to ground. By the way, if you don't put this ground in here, and you click run, it'll probably give you an error and say something about there's no reference to ground or something like that. So just be aware of that, all your circuits need a ground. So again, for simplicity, I'm going to put 1 kilo ohms. Okay, and now I'm going to click run, and it's going to give me another window, and now you can see the currents through the two resistors are identical. Now the only reason that's true is because these resistors have the exact same value, so in theory they should conduct the exact same current. So, and then the voltage, since there's only one node, this top node here, it's all 10 volts, right? Because electric potential is the same across a node. So 10 volts here is the same as 10 volts across, let me see, across this resistor, and 10 volts across this resistor. So both these resistors have the same voltage across them, so they're going to conduct the same current, right? In this case, it's going to be 10 milliamps. And if you sum those currents together using Kirchhoff's current law, you'll realize that, well, as it says here, the current through the, in this case, voltage source is 20 milliamps. So that 20 milliamps is flowing this way. And now, since these resistors have the exact same value, that current splits at this node, and 10 milliamps goes down here, and 10 milliamps goes down here. And if you notice that 10 milliamps times 1K is going to give you 10 volts. So you need that 10 milliamps here and here to maintain that same voltage across this node. So everything's kind of connected together. So that's pretty much it for the parallel network. The only other thing I can do, if I can make this a little more interesting, is I could right-click this resistor and I could set it to, say, let's 3 kiloohms. So now I have one resistor at 3 kiloohms and one at 1 kiloohm, and the same voltage source. Now I can click Simulate Run, and it'll pop up with another window. And it'll say 10 volts at that top node, so that's good, that's what I expect. But now my my current through each component has changed. Or it's changed to the new resistor because that resistance value has changed. So I have 10 volts across a 3 kilo ohm resistor, and that'll give me 3.3 milliamps, or 0.003333 amps, right? And then the current through the other resistor, the 1K, stayed the same, since I have the same voltage across the same value resistor. So that's pretty much it. You can play around with this. You can change the voltage source. Let's say I change it to 5 volts. And by the way, you don't need the volts in here. A 5 is the same thing as 5 volts. You can click Simulate Run. If you make really complicated circuits, you can actually label your nodes. So that's something important. So you can click this guy right up here. It says Label Net. And I'll call this voltage positive, meaning the positive terminal of the voltage source. And I can just put that right there. And so now if I click Simulate Run, it'll actually tell me what that node is, so it has that name. So V voltage positive, so it's a little more descriptive. So that may help you out if you're having a hard time figuring out where the voltages are. And remember that also, if you don't want to look at that window, you can just hover over a node, and in the bottom left corner of LTSpice, it'll actually give you the voltage at that node. Similarly, if you hover over a component, a resistor, or a voltage source, it'll give you the power dissipated by that component, which we don't really need to worry about right now. We'll talk about power later. And it also gives you the current that's running through that component. So in this case, for the 3 kilo ohm resistor, that's 1.666 milliamps. Okay, so that's about it for this video. Hope you found this useful. And